Okay, so today we're going to be talking about something called BFS and DFS. So these are basic coding algorithms that you learn probably in your first or second year of learning coding. So BFS and DFS are algorithms that have to do with something called pathfinding. Pathfinding is, well, self-explanatory. It's finding paths. So all of you have probably seen something like this before, right? There's a bunch of paths, and there are two chosen points, and you have to find the shortest path given between these 2 points. This is the type of problem that BFS and DFS, well, specialize in. So let's first try and solve this ourselves. What is the shortest path between these 2 points? Anybody have an answer? I'd be worried if you didn't have an answer. Okay, I'm going to assume everybody knows the answer. So let's turn on pointer. Hold on. Hey, everybody sees this? Yes, they do. So we can go from here and here. We can go from here and here, and we can also go from here, here, here. So we, as a person, know that not only know that there are more than one short path, there are actually 3 shortest paths, and they have unit length of 3, assuming that each path has unit length of 1, right? That was pretty easy. So now I want you to, I wasn't going to draw like a fully like a full path on a computer because that'd be stupid. So I want all of you to imagine a really complicated path. So path so complicated so you can't like really find the path directly. So the human brain is an amazing thing, but it has its limitations, and such that we are really good at thinking, but we absolutely suck at something called blunt work. We commonly call it 노가다. Yeah, we suck at that. Computers, on the other hand, are very good at blunt work, but they are absolutely trash at thinking. So what BFS and DFS does is it just takes those two and just put those together. That's how BFS and DFS are born. So BFS and DFS are algorithms. So let's look at what an algorithm is first. So I researched a lot about algorithms, and I compiled a bunch of data and statistics, and I put together a beautiful diagram that took like 30 minutes. I hope you enjoy. That's the algorithm. So you put an input inside an algorithm, it does janky stuff, and it spits out an output. That's how all algorithms work. So since BFS and DFS are algorithms, we just put, for example, let's say we have this path here, and we put this path inside the algorithm, and they just spit out a path, right? Who sees a problem here? And it has something to do with this path. Okay, fine, I'll tell you. Anybody have an idea how to input this into an algorithm? How will we tell the computer information about this path?
Well, you could generalize it into like a series of numbers, right? Like columns and rows.
Okay. So let's wait. Okay, so then let's say we had like a 4x4 rectangular array, and one of the columns are missing. So then we just specify which column of which row is missing, like something like that.
I guess so.
Okay, actually, I didn't think of that. That's one way, I guess. But what if it's not a rectangular array? What if it's like, I don't know, a pentagon with like a star inside? Then how would you organize into rows and columns? But short answer is it's very hard to. So there's a way that coding guys developed to input all the necessary information about a path. And we basically turn this guy into this guy. So this is called a graph. A graph is a compilation of nodes and edges. These are nodes, these circular guys are nodes, and these lines are edges. And so each path that is here, if you count, there are 1, 2, 3, 4, 5, 6, 7 paths. And these paths get turned into edges. And intersection of these paths, which are these 6 points here, get turned into these 6 nodes. Now, how does this help us? Well, we can first label each node with, well, anything. I just label them alphabetically. You can label them whatever you want. Numbers, doesn't matter. And then what you can do is you can save information of which node is connected to which node. So for example, if we have node A, we can say, okay, node A is connected to node B and node D. So if you see here, we have the 6 nodes here, and inside node A, we have node B and D. This means that if we go to node A, we can go to B and D. Vice versa, if we go to B, we can go to A, E, and C, and so forth for all these 6 nodes. Now, if we have this, we can perfectly recreate this left-hand side graph here. Now, it's not going to look exactly the same as this. That's because I purposely organized this into like squares. It doesn't have to be perfect squares. As long as the nodes are connected to each other in the same way, it's considered the same exact graph, and it's considered the same exact path. So this data structure you see here is something called the dictionary. I believe June mentioned this very shortly before. You don't have to worry about what a dictionary is. It's something in Python. It's a coding data structure consisting of keys and values. Think about a normal dictionary, okay? Everyday dictionary you have in your house, hopefully. Let's say you want to search up the word hello, right? You search the word hello. You want to search up the definition of the word hello. What do? You go inside a dictionary, you look up the word hello, and under the word hello, or rather inside the word hello, you have the definition, right? So you can think of these A, B, C, D, E, F guys as hello, and these B, D, H, C, as search of these guys as the definition. You search up the node inside the graph, and the graph returns to you the definition, aka the node you can go to. So if I search up A, it returns B and D. If I search up B, it returns A, C, and E, and so on. So it's very handy because now you have all the information. You can quickly search up all the information you need. So that's what a dictionary is, and it's very, very useful. Now, some of you might be wondering, oh, Raymond, you can go from A to B, and you can also go from B to A. So I have A to B here, and I have B to A here. Isn't this repetitive? It's the same path anyway, right? So why am I repeating two stuff again? It's unnecessarily. I have 2 times the necessary information. That's not exactly the case. See, you can go from A to B, and you can also go from B to A, right? But there are paths where you can only go from A to B, but you can't go back from B to A. So actually, all the edges have these arrows that are hidden. These are arrows that like determine which way you can go. So if all of these are 2-directional arrows, then there's no point drawing arrows. So we just like get rid of them. But let's say we have a path like this. We can go from A to B, we can't go from B to A. Then this would change like this, where previously we could go from A to B and B to A. But here we can go from A to B, but we can't return from B to A. So we have to go like something like A, B, and then B, E, E, D, D, A. So then we go like A, B, B, E, E, D, and then D, A. And then we could return back to A. So this is not repetitive. It's actually a very efficient way of storing data. So now we know how to input a path into a computer, right? We use graphs and we organize it into a dictionary. That's it. So now let's talk about DFS and BFS. I'm going to talk about DFS first. So DFS is short for depth first search. In Korean, it's called deep user 탐색. And I'll explain the significance of the name later. Let's just see what it does. So here I have recreated a random path. It's not random, but let's just suppose it is. So we want to go from green point to red point. Okay, so I'm going to like simulate what depth first search does. So depth first search is a really stupid way of finding a path. What it does is it just starts at this point, okay, and then it chooses a random point that this is connected to. It's not technically speaking random. It's whatever you put first in here, but for all intents and purposes, it's random. So this guy, let's say, chooses this guy. Okay, he's like, hey, is there any node that I can go to? Yes. Okay, choose a random one. Let's go here. Now it checks, is this the node I want to be in? The answer is no. I want to be in the red point. This is white. Okay, then is there any other node that this is connected to that I can go? Yes, I have these two, right? I already visited this point, so I don't want to go back here. So are there any other points that I haven't visited yet? Yes. Choose a random one, go here. Repeat the same process again and again. Is this a point I want? No. Is there any place I can go? Yes, go here. Is this a point I want? No. Is there any other place I can go? No. Then it does a U-turn and goes back here. And then it repeats the process, but it already checked if this was the node we wanted to be in, and the answer is no, right? We don't have to do that again. That's repetitive. So we just move on to the next point. Is there a point I can go that I haven't visited before? I've been to here and here. I haven't been to here. Let's go here. Okay, is this the point I want? No. Rinse and repeat again and again, again, and again. So let's go down the second path now. Okay, goes here. This is the point I want. No. Go here. This is the point I want. No. Okay, go here. This is the point I want. Yes. Okay, DFS is done. This is our path. Anybody see a problem here? Well, it's not a problem per se, but anybody see something that is a bit left to be desired?
It's not the shortest path.
Yes. We have an obviously short path here that we humans, as beautiful animals, can actually see, and the computer, or rather DFS, is absolutely stupid and it can't recognize it. What DFS does is it returns a path. And that's it. It returns a path. It doesn't care if it's the shortest path. It doesn't know. It just finds a path. And if you can't return a path, it says, oh, there's no path that exists between these 2 points. So that's the problem with DFS. It returns a path, and it's fairly simple and not efficient, but it's very, very simple to code. but it has its limitations. So that's DFS. So you kind of see why it's DFS, right? Why it's depth first search. It goes as deep as it can into one random route, and then just repeats it, going in every single different route until it reaches its point. So you can think of it like a column, like with water, and there's like a fish swimming inside. You have like a long ass stick, and you just shove it in as deep as you can in random directions until you hit the fish. It's not efficient, but it gets the job done. That's why it's depth first search. So let's now look at BFS, breadth first search. But before we do that, we have to learn something called, oh yeah, right, I made this beautiful diagram here. So this is what it does in simple terms, not coding terms. So it repeats this forever until it like hits the point. This is what I explained before. We don't need to look at this. So let me first explain something called Q first before going to BFS. Q is also another coding concept, but you don't have to like hang on to the coding part. It's fairly simple. So in a queue in real life, what is a queue? Like in a shopping mall, if you go to a shopping mall, like there's a queue, right? Hopefully before the shopping mall opens, there's like a line in front of the shopping mall waiting to go in. Whoever lines up first gets to go in first. So the first person to line up is the first person to go inside the shopping mall, right? It's the same exact thing here. It's a line. Crap. It's a line. So, so if we put something in, okay, we can put something out. Pushing something into the queue is called pushing. Putting something out of the queue is called popping. You push something in, we pop something out. Okay, these are actual coding terms, so I'll be using these from now on. So let's say we push in something into the queue and we push in another thing. Let's say we push in A and then we push in B. And then we pop the queue. Then A is going to pop out first and then B is going to pop out first. If you pop it again, that is. If I put A and B, if I push A and B in and I pop it, A comes out, right? And I have B in. So now I pop it, I push in C and then I pop it again, B is going to come out. Pop it again, C is going to come out. It's a very simple concept. It's just a line, right? That's Q. So now let's look at BFS because Q is used in this BFS. BFS stands for breadth first search, otherwise known as 넓이 우선 탐색. It's, again, you realize the significance of the name after we explain what this is. So here I have recreated the same exact path, except for one minor detail. I added this little line here. I did that for emphasis. I'll explain later on. And I also labeled these points to like make my life easier. Why do you do this? Okay, so we want to get from point A or node A to node F, right? So what BFS does is it kind of looks like this. We have a graph on the left, well, not physically on the left, but we have a graph, and then we have a queue, and then we have something called parents. Just ignore what parents are for now. Just don't look at this. Don't look at this. Ignore this guy. We're going to talk about this later. Ignore this guy. We're going to look at the queue. So we have a queue. We push something into the queue, and as we pop it, it's going to come out into this square. And then we can use this, whatever is inside the square, for whatever you want. Okay? So let's start. We first start by pushing our starting point, in this case A, into the queue. That's it. Again, don't worry about parents. We're going to go into parents. Just we push A into the queue, and that's it. That's our first step. We do nothing else. And then for the second step, what we do is we pop whatever is inside the queue out. In this case, A. So we pop out A, and as we do so, A is selected, as you see here. And then what we do is we push in all the points, all the nodes that are connected to whatever's popped out. So in this case, B and C are connected to A. So B and C are pushed into A. Again, the order of which it goes into the queue is completely random. It's not, but it's random. So let's just say it goes into alphabetical order, and let's say B goes in first, right? So B and C goes in first. There are no other nodes A is connected to. We're done here, right? We're done. Then we repeat the same thing again. We pop the queue. B comes out, right? And as we pop the queue, P is selected, and now we input or push all the nodes B is connected to. Now, A and C I colored purple because we already appended this into the queue once. If you see here, we put in A already. So technically speaking, we already considered A, and then we also considered C. So if we already put it into the queue, there's no reason to put it into the queue again. So we just don't. We leave this two, and we input or push in new nodes, D and E. So D and E are added here. And then we just continue this process again and again. So we pop out the next one, C is selected, and then we put in F and G because A and B are already considered, and we're done. Do the same thing again and again until something fun happens. So selected E, we input H and I, done. Selected E, we input J, and then we select F, right? Because F is next in the queue. Now F is the point we want. So we stop here, we're done. This is what we want. The program, the BFS algorithm stops. So it's either the BFS algorithm is either going to run entirely until it like reaches the point we want, or it's going to run until there are no more nodes left to check, in which case it's going to return null, as in there is no path that exists. So BFS, if it returns the point we want, F, then we know, oh, there is a path between A and F. The problem is what, right? So what would the path be? How do we know what the path is? This is where parents come into play. Let's go to the beginning. Let's go to the beginning again and let's see what parents does. For those of you people that did not listen to me, I actually looked at parents. You kind of have a gist of what this does. So as we input every node into the queue, we get something called parents. So if you see here, we inputted B and C into the queue. We pushed it into the queue because of A, right? We popped out A and we used A, and since A is connected to B and C, we added B and C into the queue. So we can say that B and C are children of A, and A is the parent of B, as in B and C exist in the queue because of A, just as how we exist because of our mother and our father, our parents, right? B and C exist in the queue because of A. A is the sole reason why it's here. It's the only existence why it's here. And then, if we repeat this again, D and E came into existence because of B. The parents of D and E are B. Similarly, we repeat this again and again. F and G have parents C, and et cetera, et cetera, et cetera. So now, after we get F from the queue, we can look at the parents. We can look at the parents of F, right? So we first start at F. What's the parent of F? Well, the parent of F is C. So we know that in order to get to F, we have to get from C to F. C is the parent of F, which means that we can go from C to F. So then the path would become C to F. Now we look at C. What's the parent of C? Parent of C is A, right? Because we go from A to C. This would be the path, right? We go back using the parents as guidance, and we retrace the path that we took. So we do this again and again until we reach our starting point. In this case, our starting point is A, so we just stop right here, and we have our path A, C, and F. That's how BFS works. And what it does is it returns a path from your two desired points, but it does something else. This is fairly complicated compared to DFS, right? It has a bit more stuff in it. So you may be wondering, what's the point of all this stuff? Well, the point is that it always returns the shortest possible path. Or rather, well, there might be multiple shortest paths, right? So that it returns a path of minimum distance, always. Let's look at how it does this, right? So if we see here, we first pop out A and we input B and C, right? I'm going to call these two nodes B and C. I'm going to call these level 1. Okay, this is not official coding terminology. Just ignore this later. This is what I call it. Level 1 implies that you can go from the starting point to B and C in one step. That's why it's called level 1. 1 and 1. Now, from B we get D and E. I'm going to call D and E level 2. You can go from A to D and E in 2 steps, right? And then similarly, H, I, J, K, L, and M, all these would be level 3. Now, why is it important? Well, let's see here. At the very beginning, we input all the level 1s first, right? Because every point that's connected to A is going to be pushed into the queue, which means every level 1 node is going to be inputted into the queue. After that, after all the level 1s are here, then we pop out the level 1s to get the level 2s. And as we methodically go through all the level 1s, we're going to inevitably input all the level 2s into the queue. So if you see here, all the level queues are D, E, F, and G, and voila, all these 4 are input into the queue. Rinse and repeat the same thing, and now level 3s are starting to input into the queue, right? And then inevitably we reach our point. Now our points, in this case we see here, there are 3 possible paths. 1 with level 2, there's another path here with level 3, 1, 2, 3, and there's a final path 1, 2, 3, 4. So node F in regards to node A is a level 1, level 2, 3, and 4 point, right? Now that doesn't matter because we go through each level one at a time, 1, 2, 3, and so on. So we first append this F as a level 2 point. And then since we already put it into the queue, even if we reach this again, we don't reconsider this because we already put it in the once. So then this would always remain as a level 2 a level 2 point, which is its minimum, right? So inevitably, since we go through the levels one by one, it always returns the shortest possible level node. right? In this case, we have levels 2, 3, and 4. 2 is the shortest, 2 gets appended, as F gets appended as a level 2 point, and it gets pushed out as a level 2 point. And that's what the parents represent, right? So that's why we can use this certain algorithm, and then use the parents to retrace our path and get the shortest possible path. Hopefully everybody understands this point. Now, I hope you finally kind of understand why it's breadth first. Like compared to DFS, where we like shove like something in as deep as possible into a random point, random path, until we couldn't go anymore, and we just repeated it until we like randomly hit F. This one, we go layer by layer. Instead of going as deep as possible, we go layer by layer, by breadth, right? And so we input all the level 1s, and then the level 2, and then the level 3s, and etc. So this is why it's called breadth first search, and that's why inevitably we get the shortest possible path. That's DFS and BFS. Now, BFS, as you can see, we can arguably say that this is the more superior algorithm. Yes, it returns a more useful information. However, at the cost of complexity. Yes, at the cost of complexity. It has significantly more stuff than DFS, and this is reflected in the actual code. So I actually try to write DFS and BFS code in Python, which is my language. Not good at it, but it's the only thing I can do. So again, this is not the best. This is not the best code. I can shorten this so much more, but this is a general idea of how, like the lengths between the two. This is DFS. It's around this length, this long. BFS is about this long. And furthermore, this is a very simple piece of code. While this is kind of complex, there's a lot of stuff going in between different like aspects of the code. The DFS and BFS are quite, they have their strengths and weaknesses. Depth first search is very simple to code, but it has its limitations. BFS returns a bit more useful information, but instead you have to do a bit more work. So those are DFS and BFS. How much time do I have left? I have a lot of time. So I was originally going to explain something else called the Dijkstra's algorithm. So let's just briefly explore this. So for example, let's go way back to this very simple path here, right? So I mentioned before that we assumed all paths had a unit length of 1, right? That's not really realistic, is it? Not all paths are the same length, and not all paths take the same time to cross. Realistically, different paths take different amount of time to cross. So for example, if this path took 2, this path took 3, and this path took 4, and like this path took 10, 20, and 30, obviously it's going to be a better idea to go here than up here. Now the problem is DFS and BFS don't take that into account, right? It only cares about the number of paths. It doesn't know about the time it takes to cross each path. That's called weights. Each path has its own weight. The heavier the weight, the more time it takes. So BFS and DFS can't be used here, which is a problem because we can't use it in traffic, right? Because this would be most applicable to us in like traffic, like in a highway and like GPS, right? Because we need to find the shortest path from A to B, for example, our school to our home, right? And we want the shortest possible path, but not in terms of distance, in terms of time. We want to take the shortest amount of time. We don't care about distance, right? If there's like a traffic jam, then a shorter distance might take a longer time than a longer distance with less traffic. So that's where Dijkstra's algorithm comes in. Dijkstra's algorithm takes into account different weights between paths, and I was about to explain that here too, but that's much more complicated than BFS or DFS, so I'm not going to. But yeah, that's also another algorithm that exists. So BFS and DFS are path-finding algorithms that you can use to get the shortest path from point A to point B. Yeah, this is also applicable in mazes, right? As you want to find, well, not necessarily the shortest path, you want to find a path from here to here. So in this case, we wouldn't use BFS, we use DFS, because we don't need useless information. And if it's similar to code, then why not, right? So we turn this guy into something that probably looks like this, a collection of nodes and edges, and then from this we'd input it into the graph, label them all. There are 100 points in total, so probably not alphabets, but just like numbers or something, like A1, A2, A3, whatever. And then we'd run DFS, not BFS, to find a possible path from A to B. So yeah, that's where pathfinding algorithms can be used. Hopefully you found this just a tiny bit interesting. Again, this is directed towards middle schoolers, so it's not that hard. So yeah, thank you for listening.